Yes, I will try to obey the time. Can you hear me? Okay. So thank you, Juan Luis, and I would like to begin by thanking all the organizers of the ICM in Korea, especially the local organizers for having done such a great job organizing this huge event. I'm very happy to be here in Seoul, a long due visit, to visit especially my dear friend and collaborator, Hyun Lee. So today I will discuss ancient or eternal solutions to geometric parabolic differential equations. These are special solutions which exist for all time, t between -infinity and capital T, where t is a number between -infinity and infinity. And I like these solutions first because I'm Greek, and Greeks tend to like everything which is ancient. But especially because they're beautiful, they have often a very beautiful structure, and they also, most important, because they appear as blow-up limits near singularity. So studying these solutions often gives us new insight for understanding singularities. Let me give you a very brief outline of the talk. I will address the classification of ancient solutions to some geometric flows. For example, the mean curvature flow, the Ricci flow, and the Yamabe flow. And I will also address the methods of constructing new ancient solutions from the gluing of two or more solitons. Solitons are special solutions, the self-similar solutions. And throughout this talk, I will address future research directions and open problems. So let me give you the formal definition. A solution to a parabolic equation is called ancient if it's defined from time t between -infinity and capital T, where t is less than infinity, and it's called eternal if it's defined for all time from -infinity to +infinity. Okay. All right. Okay, thank you. So can you, do we need to press anything? Or? Yeah. Okay, go ahead. Okay. And so this is, to my knowledge, this is a terminology through our colleague and collaborator, Ricci. So solitons, which are sometimes the self-similar solutions, are typical examples of ancient or eternal solutions, and it's well known that they're models of singularities. And there is a remarkable technique which was introduced by Richard Hamilton in the early 90s, which has often been used to characterize solitons as eternal solutions which appear from a blow-up singularities, and these are special solutions which are obtained a special way and which attain a space-time curvature maximum. This is quite a restrictive condition, but Richard Hamilton has found an ingenious way of rescaling near a singularity which allows him to obtain such solutions at blow-up limits and therefore classifying them as solitons or self-similar solutions, which means very specific ones. Usually they can be characterized. Nevertheless, there are other interesting ancient or eternal solutions which are not solitons. They don't have the self-similar structure. And these solutions may often be visualized as obtained from the gluing as t approaches infinity. Remember, all these solutions come from -infinity of two or more solitons. So some pictures, two pictures that I'm going to typically appear in this talk is this picture. This is one typical example of an ancient solution. That's how it looks, close to -infinity. And this is another example that you're going to see. And obtaining more information about these ancient solutions, the behavior of these ancient solutions, and more important, classifying them, often leads to a better understanding of singularities. And the basic objective of our research work, at least in this area, is how to construct such solutions and how to characterize them among other solutions. Okay, now I'm going to go back a little bit and I'm going to start from the beginning. So let's assume that M is a complete non-compact Riemannian manifold of dimension n bigger than or equal to 2, and it's important here that the Ricci curvature is non-negative. An old result by Yao says that any positive harmonic function on M must be constant. And this is the analog of Liouville's theorem for harmonic functions on Rn. And the basic question, the most naive question is, does the analog of Yao's theorem hold for positive solutions of the heat equation? And the answer is no, by the very simple example, uxt is e to the x plus t on R. Nevertheless, Souple and Zhang in 2006 proved that if you have a positive Einstein solution to the heat equation and complete manifold with positive Ricci curvature, and satisfies this growth condition at infinity, so this means, like this rules out this example, so this is the distance of any point P from a fixed point, an origin, and you're assuming since it's a complete non-compact manifold that this is going to infinity. So if satisfies this growth condition, then U must be a constant. And if you drop the non-negativity assumption, of course, you have harmonic functions, harmonic polynomials. So to classify, to rule out those, you need to impose a very restrictive conditions, this little o of the distance function. And this proof is not extremely difficult. Is using this local gradient estimates of Li-Yao type differentiable Harnack estimates, which are appropriately scaled on parabolic cylinders, which can be chosen, you know, of a size as large as you wish, because you're having a solution that is, comes from minus infinity. Okay, now for the next, I'm going to discuss eternal solution and especially internal solutions that they appear in the blow-up analysis of the semilinear heat equation on Rn. And this is a very old model of study. And I'm assuming for the purposes of the exposition, I'm going to make it as simple as possible, that U is non-negative, and my solution at each time t will be globally in H1 over n. And I'm going to also only deal with, only discuss the subcritical case of exponents, p between 1 and n plus 2 over n minus 2. Why I'm interested, why I'm telling you about this, these are all results, is because it turns out that a lot of these equations, models of semilinear equations, of course, much more complicated than this, often have complicated nonlinearities or often systems, appear in the blow-up analysis of geometric flows. In particular, when you're trying to classify ancient solutions, and you look at what happens as t approaches minus infinity of the blowdowns of the limits of these solutions as t approaches minus infinity, then this operator plays a role. These operators of this type play a role in understanding these solutions. So that's why I'm interested in this. And a solution, because of this p being bigger than 1, of course, solutions would blow up, which for me, for the purposes of this talk, means that the H1 NOR blows up. And On performs the self-similar scaling. This is the usual scaling for this equation, the type 1 scaling. And it's a known result by Giga and Kohn that W, which is the rescale solution, at a singularity, at a singular time t, is uniformly bounded and satisfies this rescale solution, this rescale equation, which is what I write here. And therefore, if you take limits to understand the blow-up behavior of the original equation, is equivalent to understanding the behavior of solutions W as t approaches plus infinity, and after you take limits along sequences that go to plus infinity, you end up with eternal solutions of these equations, which means solutions that are defined for tau between minus infinity and plus infinity. And therefore, classifying these eternal solutions is what is important, understanding this blow-up, understanding the blow-up behavior. And this is what usually happens in even more complicated models. And just for one slide, I'm going to tell you what the classification result is. So first of all, if you look, you can look at for steady states for these equations, and constants are definitely steady states. And one is 0 and one is a specific constant kappa. And since for this equation you have a beautiful monotonicity formula, it's quite simple to show that as tau approaches plus and minus infinity, your eternal solution, if you have eternal solution that define from minus infinity to plus infinity, and you take the limits converge to a steady state. Therefore, classifying the eternal solution means classifying all the solutions that connect these steady states. And again, because you have a monotonicity formula, it's easy to deal with all cases, apart from the case which classify the orbits, which means the solutions that they connect, W equals kappa, the specific constant at minus infinity, and W equals 0 at plus infinity. And this has been the work of a very beautiful high technical paper by Merle and Zach from 1998, which says that the only eternal solutions of these rescaled equations are either the constants or they are solutions that are independent of space, and therefore they are given by this form. And this is the result. Nevertheless, it has a very simple statement, but it's a very highly involved paper, especially because you're dealing with a non-compact space and you're trying to find a uniform behavior, and you get into trouble. So elliptical analogs, so in this result, in some spirit, it's in a similar spirit to the well-known work of Giddens-Nier, Nirenberg, and Verestick and Nierman, among others, for global solutions, for classifying the global solutions to the elliptic equation WU, Laplacian U plus U to the P equals 0. Oh. So, I forgot to put my cup last week. So, now I will just now start discussing, just give me a second. I will now start discussing geometric flows, and let's start by the curve shortening flow, which is one of the simplest geometric flows. So what is the curve shortening flow? Again, I'm doing the simplest possible case, which is a curve which is like the boundary of the yellow domain on the plane, embedded on the plane, evolving by a speed which is proportional to the curvature. And nu is a choice of vector, the right choice of vector, or normal vector, the right direction that makes your equation parabolic. And for example, if you have a convex domain, nu should point inwards. And it's an old result, very old results by Gates and Hamilton, that convex curves shrink to points, and as they shrink to point, become more and more circular. And an even more interesting and surprising result by Grayson, especially when it was proven long ago, from 1987, that says that gamma t, the curve, does not develop any singularities, even if you start with a very non-convex curve. Not only that, but something much more complicated. It will evolve, it will not develop any singularities before it becomes strictly convex. And so we thought, myself and my collaborators, Natata Sesum, who is here, she is also speaking in the geometry section, and Richard Hamilton, we were interested in classifying ancient solutions, in particular the Ricci flow. So we thought that we would first do that as a toy model, because of course it's a simpler equation. So the problem that is classify ancient compact closed curves, embedded solutions to the curve shortening flow. Now, it's well known that the curvature kappa, in terms of the arc length, which of course depends on time, so it's not an independent variable, satisfies a very simple equation, It's not as simple as it looks, again, because S depends on time. Nevertheless, it's a semi-linear equation. And a definition that will come up all the time during the talk is what it means a solution of this flow to be an ancient solution to be type 1 or type 2. And type 1 in this case means that as the maximum of the curvature as t approaches minus infinity multiplied by the square root of t is finite, otherwise is type 2. So somehow the usual type is the type 1, then usual type is a type 2. And examples of a type 1 solution is the contracting circles. An example of a type 2 solution is the unguided ovals, or paper clips as we call. And these are ancient convex solutions which are not self-similar, they're not solitons. And these are copied from a paper of Angene. So this how, right, each of these curve is for a different time, and the curve, the outside curve is closer to minus infinity, and it evolves and becomes more and more circular. And so as t approaches minus infinity, this curve, let's see the outside curve, looks like two grip-gripper solutions, which is just this, and you imagine that this extends to infinity as a straight line, and the other one is the other way, that, and which are glued together. And these are explicit solutions. These are solutions given in closed form. And the theorem with Hamilton and Natasha Sesum is the only ancient convex solutions are these two cases. The proof, again, I have no proofs in this talk, but just the ingredients is simple, and it's based on the clever use of various monotonicity formulas, and also using the fact that at its singular time, the curve shortening flow, we know, like as t approaches the singular time forward, it becomes circular with very sharp rates of convergence. So we know, we have a lot of information. Okay, now you may ask, why did you assume the convexity assumption in your theorem? Actually, there do exist solutions that other solutions, and we believe that that's not the only example, that they're ancient and non-convex. And Angene has presented a YouTube video, you could Google it and find it, and of a solution that looks like this. So the solution is again the boundary of the yellow region, and this is at a given time t, and as t approaches minus infinity, winds more and more, and if you go forward, it unwinds and eventually becomes circular. Now, this is not a proof, but Sigurd Angene is currently working on a rigorous construction of the solutions, and I'm sure he will have them constructed soon. Now, again, the curve shortening flow is an easy equation. The higher dimension analog of the curve shortening flow is the well-known mean curvature flow. And again, I'm considering only embedded hypersurfaces of dimension n, let's say in Rn+1, moving by mean curvature. And it's a well-known problem in the field to provide a classification of ancient compact and convex solutions to the mean curvature flow. Again, we impose convexity, otherwise you have many examples. Mean curvature flow is one of the flows that has a very rich class of singularities and a very rich class of solutions. So, and all the result, or nice result by Xujai Wan from a beautiful paper that deals with ancient convex, with eternal and ancient convex solutions of the mean curvature flow, in particular classifies the flow down in space-time as t approaches minus infinity of solutions, ancient convex solutions that sweep the whole space. And he classifies them as either spheres or cylinders or double planes. And now, very recently, Ben Andrews defines a beautiful non-collapse conditions, which is in the same spirit of Perelman's kappa non-collapse condition, which more or less means, with a picture, that if you have a domain, let's say in Rn+1, and you consider its boundary, which is a hypersurface, then at its point P, you can put a ball from inside and outside, interior and exterior ball condition, of radius a constant over h of p, the mean curvature of your surface at the point P. So a solution to the mean curvature flow, let's say even a smooth solution that satisfies this condition in a uniform way, so alpha is like a fixed constant, it's called an alpha-Andrews flow. Now this is a restrictive condition in the sense that it rules out exotic examples and other solutions. Nevertheless, it's a good condition, at least to put for, to distinguish. And there's a Haushofer and Kleiner prove that any ancient alpha-Andrews flow is convex at its time. Now, Angenent, again, formally constructs, with giving precise mass asymptotics, ancient, compact, radially symmetric solutions to the mean curvature flow, which as t approaches to minus infinity, again they look more and more ellipsoidals. They look like this, cylinder in the middle, translating solidon after rescaling, everything is after rescaling at the tip, and a huge intermediate region of elliptical behavior. These are mass asymptotics. Now, we knew that those solutions existed long ago from a paper of Brian White of 2003. Nevertheless, he had no details, and Haushofer and Herskovits in 2013 established the existence based on the ideas of Brian White. And in a work in progress with my collaborators, Angenent and Natasha, is to establish the geometric properties now of all alpha-Andrews ancient compact solutions, even under rotational symmetry, and characterize all of them. And you may say, okay, you put so many restrictions, and it's true, but believe me, it's still a very difficult stuff. So we're just trying to understand how that works. And okay, so Juan Luis, could you tell me how much time more I have to?
You're going through 23 minutes.
23. Okay, I have other 20 minutes. Oh, I have plenty of time. Okay.
Yeah.
All right, I finish early, which is good, I think. Okay. Now, I will next jump to another flow, which is the Ricci flow, and I will discuss the classification, classification and examples of ancient compact solutions to the Ricci flow. And let me, define the Ricci flow for you that you're not familiar. You consider a complete manifold, M, and for the purposes of this talk, will be compact, but in general, it's a complete manifold. And let G be a Riemannian metric defined on the manifold. And you consider the evolution of the metric by minus twice the Ricci curvature. And this is a flow which was introduced by Richard Hamilton in his seminal work in 1981, I think, it was the first work. And he, back then, from the beginning, he had in mind the geometrization conjecture of William Thurston. And what is interesting, what he had in mind, and again, combining analytical and geometric techniques. And there have been a very huge number of results in the Ricci flow. I just, because I don't have time, I just mentioned the breakthrough results of Richard Hamilton and Grigori Perelman, who eventually proved the geometrization conjecture. And again, many other important works. So now, so Perelman himself constructs a solution of the 3D Ricci flow and asks what is the classification of ancient compact solutions. But let's go one dimension to the 3D Ricci flow, but let's go one dimension down first, start to understand, and discuss ancient compact solutions to the 2D Ricci flow. Okay. So now again, for the moment, I'm going to consider an ancient solution that comes again from minus infinity, of the Ricci flow on a compact manifold in 2D, and ancient mean again that is defined from minus infinity to a time capital T. And in 2D is very special because all the information on the curvature, on the Ricci curvature, is given by the scalar curvature. And so the Ricci curvature is the scalar curvature multiplied by the metric. And it's a known result by Hamilton and Chow that after renormalization at the singular time t, the metric becomes spherical. And the problem again is provide a classification of all ancient and compact solutions. Now, let's consider the spherical metric, and let's parameterize again, because it's 2D and it's spatial, the evolving metric as a conformal factor u multiplied by the standard metric on S2. This is the limiting metric, what you see at time capital T. And then you obtain the Ricci flow becomes equivalent to a very nice fast diffusion equation, a logarithmic fast diffusion equation on S2. And it's natural for us that working on these diffusion equations to consider the pressure function. It's called pressure because in the case of the porous medium, it's actually the pressure, the actual pressure. And in this case is U inverse. And the pressure function satisfies this equation. Now, again, we have type 1 and type 2 solutions. And the type 1 is the usual type, so the curvature has the usual kind of bound as t approaches minus infinity, and the type 2 has the unusual bound. And what are the examples of type 1 and type 2 solutions? Now we have two explicit examples. The one is the trivial, the one that is independent on t, the one when you write it, sorry, it's independent of space when you write it as a metric on Sn, so which corresponds to contracting spheres. And the type 2 solution is the so-called King-Rosenau solution. You don't really need to remember this formula, just it's explicit. And as t approaches minus infinity, again, it's the same picture and keep putting. So it's it resembles two cigar solitons, one and another one, back to back, which are joined by a cylinder. And as t approaches minus infinity, that moves to the one side and that moves to the other side. And eventually they disappear, and you see the cylinder in the middle. And these King-Rosenau solutions are not solitons. For this reason, when you try to classify them, it's harder than has been. And a theorem jointly with Hamilton and Natasha's session is that the only ancient compact solutions of the Ricci flow on S2 are these two examples. Now, this is not as an easy result to prove as the curve shortening flow. It involves many ingredients. A monotonicity formula, which is not a standard type, which allows us to pass the limit as t approaches minus infinity, combined with a priori estimates, geometric arguments that allows us to classify the backward limit as t approaches minus infinity. That's the hardest part. Maximum principle arguments in very special quantities that allow us to characterize the King-Rosenau solution, and an isoperimetric inequality that allows us to characterize the contracting spheres. Now, what makes this problem hard, among other things, is because when you take the limit as t approaches minus infinity, the curvature becomes zero almost everywhere. Nevertheless, it's not zero everywhere, and at these tips, the curvature has a discontinuity. Therefore, all the which corresponds to the PD becoming singular or degenerate, depending how you see it, which makes life more complex. Okay, now the 3D Ricci flow. Again, not much is known, unfortunately. It has been a long-standing open problem in the field. What are the ancient compact solutions of the 3D Ricci flow? And this was right. And Perelman constructs but it's not in an explicit form. He constructs solutions which are the analog of the King-Rosenau solution of the 2D Ricci flow. And these solutions are of type 2, like the King-Rosenau, and they satisfy again this kappa non-collapse condition along the same line, the same flavor as what I told you about the Andrews alpha non-collapse condition, which has been used a lot in Perelman's work. And he questioned whether these are the only two kappa non-collapse solutions. We believe that this is true. Nevertheless, it's not known. And there are other collapse solutions which have been constructed long ago by a physicist, Fatih. Apparently they're in closed form, and apparently these solutions tend to be important in string theory, but I must say I have tried to find information, accurate information, and haven't succeeded. Now there is only one result of Bradley, Whiskey, and Sinistrati, where they present a pinching curvature condition which characterizes the contracting spheres among these 3D Ricci solutions, but this is a the pinching curvature condition is very restrictive. Okay, now my last flow, we're almost there to the end, is the Yamabe flow. And so what is the Yamabe flow? I'll give you a very short background. So you consider a compact manifold without boundary, a metric G0, and let's say R is the scalar curvature of a metric G, which is conformally equivalent to the background metric. G0 is our background metric, G0, and this is the conformal factor. And again, Richard Hamilton, I think before 1999, although his communication was in 1999, introduced the Yamabe flow, which is the evolution of the curve of the G, of the metric G by the scalar curvature multiplied by the metric, as a parabolic approach to solve the Yamabe problem. Shortly after he had this idea, Ricci resolved the Yamabe flow by elliptic methods. Nevertheless, the complete convergence of the flow, which will prove the Yamabe flow, the Yamabe problem, remained open for many years until the great work of Simon Bradley, I think it was his PhD thesis, who proved actually the convergence of the normalized flow to a metric of constant scalar curvature up to a mild technical assumption in higher dimensions, solving therefore the Yamabe flow as Hamilton imagined. Previous important works, Hamilton, Chow, Yi, Svetlik, and Stroop. And I would like to briefly discuss now ancient solution of the Yamabe flow on Sn. Again, the simplest possible case, this is a conformally flat case. Nevertheless, you will see there are many solutions. And if you, in terms of the conformal factor, you have a nice fast diffusion equation. And again, the definition of type 1 and type 2, a certain growth assumption on the rate of vanishing, the bound of the rate of vanishing of the Riemannian curvature. And the same question, can we classify these solutions? And what are again examples of type 1 solutions of the Yamabe flow on Sn are the contracting spheres, again, right, they're always there, and the King solutions. And the King solutions are non-similar solutions in closed form again, which were constructed long ago by King, of course not knowing that this is the Yamabe flow, not knowing or not being interested. This is the Yamabe flow. He was just interested about the fast diffusion equations. Now, this, how did you construct the solutions? I didn't put it up. He looks at this expression solution is kind of interesting. He projects, he looks at solutions of the fast diffusion equation on Rn, and he considers radially symmetric solutions, which are polynomials, typically of an applied mathematician. It's the polynomials in R, which is the radial variable, with coefficients that depend on time. And you get like in this dimension, when you just plug in and try to construct a solution, you stop in degree 4. You see that there are only, like you can construct explicit solutions like that, of which are, actually they're just polynomials of R of degree 4. One of them, special, is the spheres, and the other one are the solutions. And again, this is the same picture that I have been putting, which is good because my husband helped me with the pictures, not knowing how to do them, so he didn't have to work hard. And they resemble the King-Rosenau solutions of the 2D Ricci flow, but this time they're type 2, they're type 1. Why they're type 1? Because the solitons that you see at the two ends are type 1 self-similar solutions. Now, the problem is provide again the characterization of the classification of ancient solutions which are conformally equivalent to the metric on the standard metric on Sn. Again, in terms of the PDE, this is a very concrete problem. Classify the ancient and smooth functions V defined on Sn of this diffusion equation. And the first question is that are the contracting spheres and the King solutions the only type 1 ancient solutions? And what the question 2, are there any other type 2 ancient solutions? Now, you remember that in the 2D Ricci flow, which can be seen as the analog of the Yamabe flow in dimension 2, we have the classification says the only ancient solutions are the contracting sphere and the King solution. Right. So it makes sense that we ask this question. Nevertheless, in this case, we have many more solutions, it turns out. And so in a joint work with my collaborators, Manuel Delpino and Natasha, again, we construct ancient solutions of the Yamabe flow on Sn, which converts as t approaches minus infinity to a tower of spheres. So you can put as many spheres as you want, 100, 1,000. As t approaches minus infinity, they look like that. This is the rescaled flow, right? Because you need to rescale. Now, a little bit further away from minus infinity forward, they develop a little neck. And as you go to the singular forward, they become spherical. And the curvature operator obviously changes sign, and they are of type 2. Now, how do we obtain such solutions? It's a very technical work, and I'm not planning to discuss it, and I don't have time, of course. But our construction can be viewed as a parabolic analog of the gluing technique, which has been used in the past for many geometric elliptic settings, and elliptic settings especially connected to the semilinear equations. And in terms of the geometric elliptic settings, because there are a lot of other works involving semilinear elliptic equations, I would like to mention the pioneering works of Papoulas. He was the first who was doing this between 90 and 95, and other important works of Mazeo, Packard, Pollack, Uhlenbeck, again, among many others. And now, our example, to our knowledge, is the first time, to our knowledge, that a parabolic gluing technique was introduced, and we think that this technique can be potentially used to construct ancient solutions in other geometric flows. And in fact, very recently, Brenda and Papoulas, 2014, they used gluing techniques to construct new ancient compact solutions to the 4D Ricci flow. This is a new work, and it's very technically and beautiful. And the last slide is, okay, we have weird examples. And by the way, we think that you can also construct those towers of bubbles in a non-radial fashion. Nevertheless, this paper was already very technical, and I don't think we have the patience to go back and do the non-radial case. But nevertheless, you can ask the question, are the contracting spheres and the King solutions the only example of type 1 ancient solutions? And in a work in progress with Delpino, King, and Sensu, we prove actually there are infinite many type 1 ancient solutions. We work on proving, actually we haven't finished, infinite many type 1 ancient solutions which are obtained from the gluing of solitons. And they look again like the King solutions, but they're not in closed form now, because the solitons are not given in closed form. So the conclusion is that you have many solutions, and most likely you have no hope of classifying, or maybe you don't want to classify them, or you don't want to spend your time. Just to conclude my talk, we discussed ancient solutions to geometric parabolic PDE. We think that they are important. Understanding them is important because they often examples of singularities, and even in the case that they're not examples of singularities, understanding their classification gives us better information about the singularities. Now, the only existing so far results, including ours, of classification of Einstein or eternal solutions rely on the fact that we know the exact form of the solutions. And what means that we eventually find a quantity that it's vanishing on these special solutions, and we try to prove that this quantity is zero and recover the solutions from knowing the quantity. And another interesting future direction is develop, that's what we're trying to do, for example, in the mean curvature flow, is develop new techniques that allow us to characterize and construct other types of Einstein solutions which are not in closed form. And I would like to close by thanking all the organizers of this huge event, especially the Korean people who have been so great in organizing. My collaborators in projects related to this talk, and also some similar projects that I haven't had the chance of talking about: Anginet, Davila, Delpino, Hamilton, King, Natasha Session, who is here, and Jay Wei. And to my Korean and dear friend and collaborator, Kiam Lee, who is also here, he's speaking tomorrow, for a long friendship collaboration. And to NSF for supporting this work, and to my institution, Columbia University, and of course to all of you. Thank you.
First of all, ευχαριστώ πολύ, Toti. This is a gift from the organizers for our distinguished speaker.
Oh, thank you very much. Thank you.
And this is to get her in good mood. You can ask any question, and she is supposed to answer. Do you have any questions? Okay. Let me ask you this thing. There are ancient solutions and eternal solutions. Is there any way of telling any quantity that tells that the ancient solution will live forever?
Any ancient
some ancient solutions blow up in finite time.
Yes.
Or do something. And other ancient solutions can live forever, so they are eternal.
Yes,
is there any special quality to be eternal?
Not really, no. I mean, it's the same thing asking, is there a special quantity that allows you to know whether a solution of PD will blow up?
Yeah.
Sometimes there is a monotonicity formula, an energy that is decreasing or increasing, whatever, something. But usually it's not, you know. So that has to do more with the long-time behavior of the PD,
so
and not
different.
really. Yeah, because you see, what we're interested mostly is that the solution is defined all the way from minus infinity.
Yeah.
Now, for the purposes of the classification, either goes to plus infinity or to finite time. It doesn't make so much such a big difference. Usually, eternal solutions. I think that's why Hamilton, who gave the terminology distinguished, come from the blow up of type 2 singularities, and Einstein from the blow up of type 1, although this is not always the case.
Okay. Now, can you give us some words about these quantities that you check to see if the solution can go to minus infinity?
Yes. I decided not to put any proofs.
Just some words.
Yes, words. For the hardest one to find was the one for the 2D Ricci flow. And in this case, we considered the pressure functions V when you write the metric as a metric on Rn. Yeah. So you have a function of x and t, more or less, and a radius, actually not radius, x is in R2 and t, and we want to show that this is a polynomial of degree 4. Okay, because once you know in x with coefficients in t, once you know that it has this form, then you can recover that it's the King solution. That's how King obtained his solution. Yeah. And so what we found is a weird quantity. Nevertheless, it's when you write it in complex form, is in terms of z complex variables, is z V, Z, Z, Z. So it's Z multiply, and then it's the third order derivative of V with respect to this complex variable Z. Now, we didn't think of it this way. We guessed it otherwise. But this is what it tends to be. And then we consider this quantity. We saw that this quantity it decreases. And then we prove that this quantity as t approaches minus infinity goes to 0. Therefore, because we also...
So it looks like a complex symmetry hidden there.
Yes, it looks so. And actually, we don't have this, it is, because it's 2D. Yeah. And it has, it's 2D and it has a conformal structure. So definitely there is.
Would you suggest to persons that investigating these kind of symmetries, hidden symmetries there,
absolutely,
that allow solutions to be...
Absolutely. And this, again, the king solutions are the special solutions. They have their specific forms and symmetry, and even rotational symmetry, which seems easy, but to prove rotational symmetry, for example, for the 3D Ricci flow, it's a difficult question. It has been a long-standing open approach.
Another question from the floor. Okay. So, thank you.